那你要讲多这些吗？还是讲这些？7:06。
Right. Now it's 7:06. We kind of late for 6 minutes, but yeah, okay. So today is our last webinar for this matter, and today our topic will be covering the last part of the uh yeah, the last part of the, I think is unitary, right, and the operators and their operators. And the second part will be the postulate of quantum mechanics, and that's covered by Jimmy. And I will be covering something that's a bit out of this, a bit just a little out of this our flow, but it's still related. Okay. All right. So let's start now. Okay.
Okay. First of all, I would like to voice out. Let me try. Hello, 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 hello. Okay. So I would like to apologize that I was late. So actually my part is done, but I want to clarify something from last week. So there was some misconcept from last week. Maybe we first talk about with unitary operators and Hermitian operators. So last time I introduced Hermitian as a unitary. In fact, they are not. Actually, in the lecture notes that I put out, there is a definition for unitary. Okay, so let me tell you what are these. So, what is an unitary operators? So, an unitary operators T, first of all, is an operator. So, operator is nothing, just a linear transformation, linear maps. Okay, how is it unitary? So, it is a unitary operator if T inverse equals to T star. Yeah. Okay. So the inverse of the operator is the adjoint. The adjoint is the inverse. Second of all, Hermitian operator. Let's call it T again. Is also an operator such that T equals to T star. So it is self-adjoint. So the other word is a self-adjoint operator. Okay, so when does this two kind of operator equal? Can you imagine? When is a unitary operator Hermitian operator? Okay. T equal T inverse. Yes. Okay, so let's try. So the claim is for T square equals to identity, T is unitary if and only if T is Hermitian. This is the claim. So let's prove it. So there are two directions here, right? Okay. Suppose T is unitary, then the inverse of T is the adjoint of T. Okay, and we want to show T is Hermitian. Okay, that is T adjoint equals to T. T adjoint. Since T is unitary, we know what? T adjoint equals to T inverse. Okay. But T square is identity. So meaning what? T is the inverse of itself. Okay. So T inverse is T since T square equals to identity. So we are done. So last time, remember last time we showed that inverse of a unit, what did I say? Inverse of an element is unique, right? So T is the element that makes T into identity. So T is the inverse. Okay. Make sense? Any question? Okay. How about the other direction? So suppose T is Hermitian. Yeah. How about T is Hermitian? Then the adjoint of T is T itself. Right. What do we want to show? We want to show that T is unitary. Okay. So that is to show that T inverse is T dot. Okay. So since T square equals to identity, right? So T inverse is what? Is T again. Okay. But T equals to T dot since T is Hermitian. Okay. So I think last week Yang Ken pulled out a poly matrices, is it? The so let me write down the matrix. So last time the whiteboard, you can write down a matrix like this, right? Poly X matrix. Okay. Is this matrix squares to identity? Is this matrix squares to identity? Can do multiplication, matrix multiplication. No? Is this square to identity? Yes, right. So if it is unitary, then it is summation. So in this case, the fixed conjugate of this matrix is itself. So it is summation. And it is T squared to identity. So this is unitary. So this is a very ideal case. Yeah. Yeah.
You assume that inverse exists.
Do I need to I mean T squared equals to identity already tells you the inverse. T equals to identity. T is the thing that makes T into identity. And then from two-sided, in other words, it's a left inverse and right inverse. So it's an inverse. Okay. Yeah, the existence is given by this T squared equals to identity. There's something that makes T into identity. Okay. Make sense? Okay. Any question before we go to the next part? Okay. All right. Let's go to next issue. So the full Hilbert space. So we haven't defined properly what is a dual of a Hilbert space is. We did define a dual of a vector space. Anyone can recall what's the dual of a vector space? What is the dual of a vector space? Hmm? It's a set. Right. What's that set? Set of what? You have a vector. Right. What can you do? Bring it to a scalar. So what are those things that bring vectors to scalar? The linear transformation. This kind of linear transformation, we give it a specific name. What is it called? Linear functional. Okay. So this is a set of linear functionals. Okay. So linear functionals. So I will write it as L from V to, let's say, our vector space is over a field F such that L is linear. Okay, I don't write down those two properties. Okay, but this for Hilbert space seems like too ambitious. Okay, so I would like to define a dual of a vectors of a Hilbert space to be a set of bounded linear functional. So what do you mean by bounded here? Huh? What do you mean by bounded here? What does bounded mean to you? Can you guess what thing is bounded here? So linear function is bounded. So how do you bound linear function? How do you bound a map? Any idea? No, not quite. Yeah, not quite. Yes. So somehow we want to give a length to the linear function. Okay, so we need to. So let's keep this. So we want to define the length of this linear functional. Okay. So um, so we say that a linear operator T from a known space to another known space. Okay. So recall that if I give you a inner product space, you can make the inner product space into a known space, and then you can make it into a metric space. Okay, so now let's talk at known spaces first. It's bounded if I can define an operator norm. Okay, so I try to measure this linear map here. So how do I define it? So what we know is we know what's the length of V. I mean, a length of element in the V or W. Okay, we try to make use of this thing. So we will define the operator norm of T by the supremum of everything in your domain, which has length 1. Okay, and then let your operator add on it. And you compute this length again. And this number is finite. Okay, in a moment, I will tell you what is sup is. So what is sup? What is sup here? Anyone know? Heard about supremum before? What is sup? Or what does this English word mean to you? Maximum. Okay, very close. Maximum. But we want to make it more how to say, more precise. Okay, because maximum is something that we can achieve, but supremum might not be achievable. Okay, so what is supremum here? So supremum here is an upper bound, first of all, and it is the least upper bound. It is the smallest among all the upper bound of the set. So you should regard this number here as a set. So let me be a little bit more precise. Usually we don't write like this, but we know that this is a set because we let t add on all v, okay, such that the length of v is 1. So it's like a unique length. Okay, maybe you will ask why unique? Why one length 1 and length 2 cannot be length 3 cannot be? Then that would be a problem to show that this actually defines a norm. Okay. So if you go and try and show this operator define a norm, then you need the length of v to be 1. Okay, make sense or not? Okay. Any question on this definition here? So you still go to your vector space there and then find your length. Yeah, but you let your operator add on some vector. Wow, these vector, these are the length 1 unit vector. So you should imagine that this unit vector is if it is a complex plane, then they are the unit circle. Okay. If you go higher dimension, then you can imagine unique sphere. So on. I mean, circle with radius 1, sphere with radius 1, and so on. Okay. So this is what bounded linear operator means. Okay. So this has a nice consequence here. So if we just consider dual space with a bounded linear functional, there's a nice consequence here called the Rees representation lemma. Okay, so what does this Rees representation lemma tell us? So for all bounded linear functional L, okay, that exists a unique vector in your Hilbert space. Okay, let's write out our Hilbert space. So this is to C. Let us just consider to C. There exists a unique vector in the Hilbert space such that your linear functional just act like a inner product. Okay. This proof is actually not hard. Okay. If we consider ourselves to be in the in a finite. Let me think. Finite dimensional vector space. It is not hard to prove. but we will use this result here. So what is this result here? So if you have a bounded linear functional, then your linear functional just act like some inner product. Okay, by fixing one variable here, v. Does it make sense? So if I want to write this in a map form, maybe I can write like this. The function. Okay, so this define a map from V to L and L. Okay, so typically we will label this V, this L with a V using a subscript. Because for every, you give me one bounded linear function now, then I can attach a unique one. A unique inner. Okay, realized by some vector in the Hilbert space. And actually this formula called rho. So this gives us a bijection between Hilbert space and its dual space. So you give me one L here, I have a unique inner product realized by some vector. Does it make sense? So I have an L here, I can map it to some V, okay, such that the inner product with V is this, give you the same thing as what L give. Okay, and this map, not just bijection, but this bijection is a linear map. So it's an isomorphism. Okay, so this map have nice property, it's linear. Respect vector addition and respect scalar multiplication. Okay. Okay. So this is how we define. So this is how we define the dual of a vector. So a dual of a vector, V star. Okay. V is defined to be LV. Okay, what is LV? Not the back, not the LV back. Is what? Is the inner product with V. Okay, that's all. Okay, last time we defined it as like a connector delta, but that's not enough to realize the whole dual Hilbert space, because last time we didn't define properly on this dual Hilbert space, so I try and bring the definition up. So when we talk about dual of a Hilbert space, we just consider the set of bounded operator. Or sometimes we will say that it's a continuous dual. Because there's a theorem that if it is continuous, then it is bounded. Wait, let me think. Am I talking about the wrong way? So if it is bounded, then it is continuous. Yeah. When T is bounded, then it is continuous. And I also prove in the note that if Hilbert space is finite dimensional, then every operator must be bounded. Yeah, so that's why we only consider bounded linear operator here. Usually we work with a finite dimensional vector space, but maybe we'll get harder if we go to infinite dimensional. So infinite dimensional vector space is another level. Okay, so first level you come from a set, right? So set could be finite or infinite elements inside that. When you go to infinite set, harder to study, because finite set is just 1 to n elements inside that. But go to infinite, how to study? There are so many things there. So we try to put structure on it. Does this infinite set have extra structure? So the vector space we consider usually is infinite, right? Like R square, infinite, right? But they have they are finite dimensional. So meaning they have finitely many basis elements. So you can use finitely elements to generate everything, infinite things inside there. And somehow the map between these finite dimensional vector space controlled by the basis, because linear map is what we can. And then infinite dimensional become another story, where the basis itself become infinite. So how to study infinite dimensional space? We need extra structure, no? Maybe we should. And make it finite again. So this is how it goes, how the story goes. Okay. Before we take a break. Should we take a break? Any question before we go into the postulate of quantum mechanics? One thing inside the seminar, right, maybe you will feel this is just some sharing of experience. So maybe you will feel a bit easy, or like what's that? Not focusing. So what I can suggest you is you have to instead of how's that? You should first of all you should listen carefully what the speaker say, and then you should get the logic right. You try and catch the logic first. Maybe you don't understand what are all the words that the speaker say, but when they speak of any terms, right, it must be used before or after. So you need to like try and catch what's the meaning of those words. If you really cannot catch it, you should speak up. You should ask. You just ask. Okay. So make sure your logic is going on. Otherwise, you will get lost easily. Yeah. Yeah. So different people have different pace. So you need to try to adapt yourself, find a way. Because I also feel busy until I think even after not after my PhD, but before my PhD, during my PhD. So well, I mean I keep telling my student, right? So in the first year max, right, when I enter the class, right, I can only stay for 5 minutes only. The other the other 45 minutes was gone, disappeared. The next second semester I get better. I can stay for 15 minutes. And then the next 45 minutes I disappear. The lecture keep going on, but I don't know what the lecture is talking about. And then second year better, 30 minutes, and then third year 45 minutes. Okay. But still lost somehow. Definitely lost one. The clock tick until 45, but I was lost. I don't know why. Very, very, I would say very 准. Malaysian, very 准. Very accurate one. Yeah, you must lost. So something in you have to change. And different people have different reason for losing focus. Okay, yeah. So you need to try and figure out yourself. But logic is the way. And that's why we study mathematics. So there's some logic there. Even with logic, you can find maybe some flaw on the speaker. Yeah. Okay. Any other question before we pass the baton? Is everyone clear up to now? So if you're interested, right, what we discuss here is in functional analysis course, if you're interested. Do you guys know that there's a ME courses meeting this Friday or not? Yes. There's an email or what? No email, then how do you guys know? Huh? Oh, you don't know? Anyone knows or not? Okay, especially for the math student, you know or not? How do you guys know? Peter, email. Teams? Is it on the mathematics teams or not? Is it? I didn't see any. Oh, it was. Okay, when is it posted? Ah, this Friday. When is it posted? Because I try and scroll and search. I didn't see. Last Friday. Before today. Yeah, you see there's a lot of master thing. Uh, yeah, so there's a ME meeting. So this ME is for April. So if you're interested in Mac ME, you can come and listen what courses they're offering. Yeah, where can you find the link? I was looking for the link. Where's the notice? When's the notice? You guys know? 12th March. 12th March. Department of Mathematics, right? What family? Oh, I'm not in the family. Okay. Yeah, I just realized I'm not in the family. No wonder I moved to physics here. Okay. So I was not in the family. I was just in the Department of Maths. So maybe I'm the imposter. So I have to share to physics. Okay. So if physics student want to get it, I'm not sure. Is you guys got of course I give one lah. I mean, Yan Ken, are they shared? Does physics student get shared with this ME stuff? No. Is it allowed or no? Oh, I think it's online. Oh, just a link. Distribute the link. Yeah. If you interested, you find physics, find Alistair. Uh, post IG, post Facebook, post everywhere. Okay. Yeah. Okay. Yeah. Share to all your friends. Even if you are not taking, maybe you should come and see what are they offering. Okay. Okay. Let's take. Yeah. 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 So if you're interested, look for Alistair. Okay. So let's take a break. 5 minutes. 5 minutes break until 7:45, and then we come back for postulate of quantum mechanics. It's okay.
That's right. And yeah, we share to our team, seminar team.
Aku teh tarik. Oh,你要
join 那个 Teams
要吗？还是你要自己下
join Teams
？OK，你这个 recording 也放
然后就这么，然后要 proof 要 proof 我没有 proof 要 proof 要 proof。OK，我就说这个如果我是优先，然后反正咱们去 OK，我但是你可以，如果人家讲一句东西，你就可以开始想一下有可能。压力好，什么？
不要，不过好像，怎样打叉掉他那个道路？没有，我打叉他那个道路是他的电脑，我不到。
那个 bigger cursor right？真的，
嗯，
本来就 share 的。
哦，等下我 present 的那个 slide，
哦，
你要现在 share 啊？
可以 share 啊。
可以啊，看一下。
我没有 slide 哦。
嗯，
起来，这样看方式可以那个我们就可以跟可以搞这个，也两方面跟对，加这两个，再加这两个，这两个还是一方。然后我要加。然后你发现在这个免得认清楚所有的那些，但是我这是
QMPPTX，QMPPTX，
对，还好。新的一些选择应该然后感觉是一个他们那个现实动态的一个。对，就是反正对它好像如果让假设呢，好，假设你这个，我们可以放 base 取决于第一，觉得啦，那个 basis 我们 functions 可以注意，其实是它 lower space。basis 应该就是 vi 多，不是 vi 多是什么呢？就是我那天讲让 v 去。好处，就你一定是改的，这个是我们好，所以我 这个就可以告诉所有的开出所有的方程。
这个方案的话，是因为不要现在还是
因为我可以再选一个 orthogonal 的，让 basis 然后数据。哎，跟你这个 action 方程这个方程这个方程，因为你在这个 vector 的这个是 function，yeah，function from 一个 vector space，所以它也是 vector，所以 vector space 是一个 abstract 的。不是仿真方，我仿真一个呗。vector space 一个。Actually，你 linear function 也有长度的表现，有的比较。也是的。
好像会 lag，应该不会。
那可以平常的
没有 PowerPoint
完全没有写，
写什么？
完全没有写。
后面有写啊，不过呀，会多一点。
用笔吗做？
没有，不是。你看，诶，
这是什么？
好像来
这是什么？
PowerPoint 吧？
用笔吗？这不行。我一看就上面。
来，
明白了。
来。有点 lag，我要不要换 computer HDMI 可能？哎，你看我现在其实 share 这 first slide 啊，它这个是 second slide 而已。
再换一个呢？
我其实在 second slide，然后这边 show first slide，换掉很。
你呢？哦。
Yeah，for example， 这边 shows second， 我这边 shows first。
这个是因为你的问题是吗？因为你在 view 还是这样，你把那个什么 PowerPoint 的那种，一边是 view，一边是那个。
这直接是 presenter view。
presenter view。哎呦，还考一下你的，你的
有念了，
你也是在学，
那我在学。
像这个就照你的了。这个开了吗？presenter 在哪里 ？Control P 啊 ，Internet 这样啊，
我上次直接 present 都是直接插进去
就可以了没？它好像要 adjust。哦，你有没有 F8？啊，都没有反应。还是你要 extend duplicate 就是这边一个，那边一个，就 extend 是你看到什么，那边就看到什么。
是
是 extend off，你要把它拉出去，你要拉出去吗？
拉出去。
Screen。Yeah，要是。
OK OK OK。还有叫什么？等一下，是飞出去。OK，可以可以。Okay, so I'm Jingyi, and today I'll be sharing with you all some postulates of quantum mechanics. And I think I will start with the motivation. It's fine. Okay, so at the beginning of this seminar, Alistair has shared with us some insufficiency of classical mechanics in explaining some of the phenomena. One of the famous one will be the black body radiation. And our goal for today is to be able to describe any quantum system with the help of postulates. So first, we need a framework for the quantum system. And with this, we have chosen the Stern-Gerlach experiment. And the reason why we choose the Stern-Gerlach experiment is because it is the simplest case for us to study. And we will see why it is so at the end of the introduction of this experiment. And if you still remember, during the first seminar, Alistair has shared with us the quantization of energy that was postulated by Planck to solve the mystery of the black body radiation or ultraviolet catastrophe. And actually, soon later that, Niels Bohr has proposed the model of the hydrogen atom that we can actually use the quantized energy level and also the angular momentum in describing how the electrons actually orbit around the nucleus. And in this Stern-Gerlach experiment, we will give another concrete example of the quantization, which is the quantization of angular momentum. And after we have introduced the Stern-Gerlach experiment, we will present a simplified setup view for us to have a clearer view on how any quantum system can actually be described from this experiment setup of Stern-Gerlach experiment. So So the following slides and also the notes that we have posted are actually greatly supported by all these resources. So you all can feel free to read up if you feel that these notes are insufficient for you. Okay, yeah. Okay, so what is the Stern-Gerlach experiment? Actually, in 1920, just a few years after Niels Bohr and Planck have postulated about the quantization, the concept of quantization, Otto Stern and Gerlach have actually designed an experiment to measure the magnetic dipole moment of an atom. So what is the magnetic dipole moment? So magnetic dipole is just as simple as a bar magnet with two poles, the south pole and also the north pole. And what about the moment? So if you have some background in physics, we have actually encountered a lot of moment of inertia, a moment of angular momentum, and the most simple case is actually the moment of force. So the moment of force actually is just a measure of how much force that we are required to rotate an object, and it can actually be determined from the cross product of the perpendicular distance from the pivot point to the force. So magnetic dipole moment is just the strength of a magnetic dipole inside this atom to align with the external magnetic field that we apply on it. So you can see actually from the diagram on your bottom right, the magnetic dipole is actually in a random orientation. But when you apply an external field, the magnetic dipole will actually try to align with itself with the external field. So these are the strengths that we are trying to measure in the Stern-Gerlach experiment. So you may ask the question, why does atom actually has the magnetic dipole moment? In fact, every atom actually consists magnetic dipole moment because every atom has an electrons. And first look at the pictures on the right, on the left first. Yeah, the atom actually consists of electron that orbits around the nucleus. So electron actually carries charge. So charge actually precesses this charge of electron. To be precise, it actually precesses around this nucleus, which is on the right of the diagram. Yeah, this is actually a closest approach of how the spin actually rotates around the nucleus. So from electromagnetism, any moving charge will actually generate a magnetic field. And so we can perceive the electron as a bar magnet, but at the atomic scale size. And how do we determine the magnetic dipole moment? Is the product of the current and also the area which is the circle that is covered by the electrons. And then we just, because we want to, here we are trying to find the relationship between the magnetic dipole moment and also the angular momentum. So we substitute the formula for the current, which is the charge per unit time, and the area is the area of the circle. And we bring in the velocity formula into it. And then this is actually the classical formula for the orbital angular momentum. So you just manipulate the equations, then you obtain this is the final form of the magnetic dipole moment that is expressed of orbital angular momentum. In fact, the classical orbital angular momentum is actually the cross product of the radius, the radius, and also the velocity. So mu, if you're using the cross product, I cross A, you find that the magnetic dipole moment is actually pointing downwards. And for the orbital angular momentum is R cross V, and it always points upward. So the direction of the angular momentum and the magnetic dipole moment are always in the opposite direction. So we'll put a negative in it. Yeah, it's not showing. Yeah, there will be a negative in it. Okay, so this is the setup of a Stern-Gerlach experiment. So how do they conduct this experiment? So first of all, you need to choose an atom, and the atom that they have chosen is actually a silver atom. the reason why they choose the silver atom is because the silver atom, if you look at the orbital shape or the electronic configurations of the silver atom, it actually consists only one electron at the outermost shell. So they can precisely determine the magnetic dipole of this exactly one electron. And yeah, so they pass the silver atom through this external magnetic field, and this external magnetic field is actually inhomogeneous. And the reason why we actually need the external magnetic field to be inhomogeneous is because if you look at this equation, the magnetic dipole moment and also the angular momentum are actually just constants. So in order to have a non-zero force that is acting on this magnetic dipole, we need to have a magnetic field that is non-constant. That is, if B is actually the magnetic field. If B is actually a constant, then the force acting on the magnetic dipole moment will actually be zero. But we actually want to determine what is the force. We actually want to determine the behavior of the magnetic dipole moment that is being experienced. Let me rephrase this. We want to actually determine the direction of this magnetic dipole moment that's being deflected on the screen. So we want a force that is acting on the magnetic dipole moment only depends on the angle between the magnetic dipole moment and the external magnetic field, because mu dot B is actually mu B cos theta. Okay. So when we send these silver atoms to this through this and one more thing to mention here is that the inhomogeneous magnetic field is actually achieved by the sharp edges of this magnet bar. And when we pass the silver atoms through this external magnetic field, the magnetic dipole moment will be shown on the screen, which is along the z-axis. Yeah. So look at the third point. This is actually the expectations that we should expect in this experiment, because we have mentioned that since the force is actually not a constant and it actually depends on the angle between the magnetic dipole moment and the external magnetic field, and magnetic dipole moment initially is actually at any arbitrary direction. So we should see a continuous deflection of magnetic dipole moment on this screen. But in fact, when the result actually show out, they only see two beams being deflected, which is the fourth point. Yeah, they only see the fourth one, and the third one is actually our theoretical prediction. Any question for now? So we want to study what is lacking in the theory, such that why is the angular momentum that we should observe to be continuous in classical mechanics turns out to be discrete in quantum mechanics. But first of all, we need to introduce these orbital shapes. If you have some background in chemistry, you might be familiar with all this, but even if you don't, it's fine, because all you need to know is that these orbital shapes are actually just the electron clouds of the atoms, of the electron cloud of the atoms. And we only need to focus on the one that are circled in orange color or yellow color. For silver atom, the outermost electron at the shell is at the s orbital. So at the s orbital, it actually has a spherically distributed symmetry, such that L, which is the orbital quantum number, equals to 0, and the orbital magnetic quantum number n equals to 0. These two quantum number are very important in helping us to determine the following angular momentum. Yeah. So the angular momentum for the boulder L is actually the angular momentum. It can be determined by the orbital quantum number. So different electron occupies different states. So they might have L equals to 1 or 2 or 3. But orbital angular momentum, we only have one component. But when it projects to the z-axis, which is the angular momentum along the z-axis, it can have multiple values because ml is actually a range of value from negative L plus 1 all the ways to L. So, and in the Stern-Gerlach experiment, we have fixed the spring to be along the z-axis. So the angular momentum along the z-axis is the things that we want to study here.
This shape is not spherical, right?
Which shape?
So how you go from the spherical shape into this thing?
Spherical shape
Oh.
to this thing. Yeah, that's a good point. This is actually an example of L equals to 2. This is not L equals to 0. So if L equals to 0, we should actually see only one component along the z-axis. Yeah, because this is only the diagram I can find online.
Yes, L equals 0 or L equals to 2?
L equals to 0. L equals to 2, I'm just trying to show you that the angular momentum along the z-axis can take different values and can take more than one values. Yeah, and this is not the correct picture for L equals to 0. If L equals to 0, we should only see one green line here because LZ just equals to ML, where ML is actually just equals to 0. Oh. In fact, we actually should observe no orbital angular momentum. Can you actually see why we actually should observe no orbital angular momentum here?
When L equals 0?
Yeah. So the orbital angular momentum, the bolded L, is actually equals to 0. But for the angular momentum along the z-axis, should have only one component because ML can take the value of 0. So LZ can actually have one component. We actually show in the next slides here. Okay, so here, take for example, L equals to 2. The orbital angular momentum will actually be 2h bar. And then we can write a range of value for the angular momentum along the z-axis. And then if you repeat this procedure for L equals to 3, I mean small letter L equals to 3, L equals to 4, you'll find that they actually obeys a pattern such that the component along the z-axis for the orbital angular momentum can only take 2L plus 1 value, which is always an odd number. But in our results for the Stern-Gerlach experiment, recall that we only get two values, which is the two possible values for the magnetic dipole moment, which is the up values or the down value. So which means that the angular momentum that is contributed to this magnetic dipole moment is actually not coming from the orbital angular momentum, but coming out from some orbital angular momentum. And they postulate this type of angular momentum as the spin angular momentum, or in simple word, is just a spin. So for the spin angular momentum, we actually introduce another quantum number, which is called the magnetic quantum number. And it can actually take only two values, which is the positive h bar over 2 or negative h bar over 2. And this aligns with the predictions. This aligns with the explanations for the Stern-Gerlach experiment results. I haven't studied that.
They just cook this thing up because of the discrete result.
Yeah, I guess so, but electron is actually a spin half particle.
I know, I mean,
Yeah.
they created this spin half for this experiment.
I cannot answer at the moment whether is it yes or no, but yeah, I can try to, yeah, I'll go back and try to find out. Why can't it be positive h bar and negative h bar, right? Okay, moving on. Okay, so after they have get this result, they know that there's such thing called spin angular momentum, and angular momentum is not continuous like in classical mechanics, but is quantized. And they actually sent a postcard to Niels Bohr, and this is actually a postcard that they have sent to him to congratulate him on the confirmation of his theory on the quantization of angular momentum. Yeah, so this is just a story part. So just now we have a lot of information about this Stern-Gerlach experiment. Now we try to break down the process and to see how we can actually use this Stern-Gerlach experiment setup to describe the quantum system that we have. And the reason why we actually choose Stern-Gerlach experiment is because from the result that we've obtained just now, it's actually just the simplest case to study. It only consists of two states, the up states or the down states. So it's actually the simplest case to begin with before we generalize it to many state system. So first, in the Stern-Gerlach experiment, we will also bring up some terminologies that's being required in explaining the postulate of quantum mechanics later. So in the first step of the Stern-Gerlach experiment, we actually prepare the silver atom. So in describing any quantum system, the first step we need is to first prepare an initial state. The initial state can be anything that's measurable. For the Stern-Gerlach experiment just now is the spin states. But on the other hand, if you want to study the motion of the electrons, the state that you need to prepare will be just the momentum. After we prepare the states, we pass this silver atom to this measuring apparatus. So we need the measuring apparatus. In the Stern-Gerlach experiment, it is the inhomogeneous magnet. And in any other quantum system, the measuring apparatus must not only be a magnet, it can also be an operator, which is some device that can actually sort out. For example, it can be a selector or a flipper. A selector is actually basically to sort out the spin states. So for example, selector for spin up, a spin out selector will only sort out the spin up atoms, and for a flipper, we actually just reverse the direction of the spin states. Yeah. Yeah. Okay, and the final state will be the quantum states right after the measurement. So after the silver atom actually pass through these magnets, we will measure what is the states of the magnetic dipole moment, whether it's in the up states or the down states. And these are the states that we call the eigenstates. So eigenstate is basically the states that is the state performed right, that is the state right after the measurement is being performed. And we also introduce a new term, which is called the measurement outcome or eigenvalue. And eigenvalue is actually just a complex number or any real number, but it actually comprises the information that can help us to determine the probability of finding a state in these eigenstates. So eigenstates you can basically understood as the possible states of a quantum system.
So what are the all possible states for H?
From the results that we have obtained, just be the up and also the down states. So spin up, spin down. These are the states that are the eigenstates. Okay, so here we move to the postulate one. Actually, why do we need postulate of quantum mechanics? Postulates of quantum mechanics actually help us to describe better on how measurement in quantum mechanics can be described with the mathematics that we have learned. So the first postulate will be the state of a physical system is characterized by a vector in Hilbert space, which just means that we need a vector in Hilbert space to describe this state of these states. And we have already introduced that state is actually just some physical properties of a system that is measurable, and it needs to be represented by vector in Hilbert space. Yeah, so these are the definitions of the Hilbert space that we have gained from the past few weeks, for the last week of the seminar. I will not read out here, but yeah. And if you have already know that the cardinality of a set, which is the number of elements in a set, is basically describe the dimension of the Hilbert space, or the dimension of the
basis of the cardinality of a basis. Not any set. Basis.
cardinality of a basis. Oh.
Basis of the Hilbert space.
Space. The cardinality. Okay. So this leads us to another statement that is for n-dimensional Hilbert space. It is spanned by n basis vector. So for basis vector, you can actually write it as a linear combination, right? So we will write the state of any quantum system in terms of the linear combination between the scalar multiplication and also the eigenstates. And then next we move on to how do we determine the probability of finding a state in eigenstates. So given, for example, we have a state that is prepared in these states. So it's being normalized. So there's a 1 over square root 2. And then how do we actually determine the probability? It's actually by taking the absolute square, showing of, for example, we want to find what's the probability of the states in the eigenstate of state 1. Then you just take the inner products of 1 and also the states. And then compute this. Then what you get is actually just 1 over 2.
But you haven't tell us how we define the inner product. How we define the inner product?
The inner product?
How we define
the bracket vector?
Yeah.
I thought we already gone through it during the seminar.
The inner product is anything that satisfies the three property. But what's the inner product?
Okay.
What's the definition? Given you any two eigenstate.
Okay, so
what's the inner product? How do you define?
So for example, this is the state. And then if you want to determine the inner product of these two states, first of all, you take the cat, the bra, the first one of the states, and you take the cats of another states. So this is actually an inner product. Or if, for example, 1 is actually in this column vector, and 0 is actually zero. Okay, then we'll be just taking the row of the first cat and then taking the column of the second one. Yeah. Yeah.
So this is one example, right? So this inner product should work for all stacks, right? So what I'm looking here is like you are just using So first of all, you have a two-dimensional Hilbert space here, right? Because you have up and down spanned by these two bases, right? So you can identify this two-dimensional vector space with R2 using this presentation. Actually, they are not equal, but there's a map going on here. How can they be equal? You just define them to be equal, but they are not really equal. They are living in different spaces.
They're equal for the inner product.
No, I mean when you write the vector 1, right, equals to 1, 0, these two things live in different space, you know. How can they be equal? They are different things. Right? One have two things, one have one thing on it. How can they be equal? They are not equal, but you are identifying them. You got me? So there's a isomorphism between R2 and this two-dimensional vector space. It's what we usually do. Any n-dimensional vector space is isomorphic to Rn.
Oh, is it? It's not in difference. It's in different space.
Different set. One and 0 is the state of atom, right? But 1, 0, 0, 1 is just R2, a random. I mean, not random, but R2. So that cannot be equal. One is a real plane. One is state of an atom. So the equal sign here is an identification.
So I shouldn't put an equal sign there.
Strictly speaking, you can't, but you need to know what you are doing.
Okay.
So you are trying to identify these two spaces here. And then what I'm trying to say is
So in that case, what is the space on the left hand side?
What is the space? Yeah, what's the space on the left hand side? So the
space on the right is R2. So right, what is on the left?
It's just a two-dimensional vector space. That's all. Not R2.
She's not saying it's R2, right?
She's equal.
The two states of the Stern Gala is the two-dimensional space, vector space over C.
Yeah, sure. That's fine. I mean, if it's over C, then C2 here. I mean, the identification is with C2, not R2. Yeah. So I mean, one side, what we call is two-dimensional vector space. The other side is a real complex plane.
No, there's no two sides. This is how we write.
I know this is how you write, but this is not valid in the mathematics, right? I mean, so this two things here. So see. All right, so this is by definition AB such that A, B, and C. This one depends.
Yeah,
this is just spanned by any two vectors.
Okay, then hang on. Who is saying?
No. When you write like this, then surely like in this form. Right? Okay, if you don't like this, then when you write 1, 0, automatically we're thinking of this space, not this kind of space. If you say, okay, I mean this is what? This is of course span of 0, 1, 0, and 0, 1, actually. But this one is anything. Yeah. This is what I want to say. When you put equal, you really work in different spaces. So I mean that's a non-trivial isomorphism here. And this isomorphism is given by what you said. So I send this vector here. Okay. So the two-dimensional vector space you consider is spanned by 1 and 0. Right. So you send 1 to 1, 0, and then you send 0 to 0, 1. Yeah, so when you need to be careful when you write equal. When you need to be careful when you write equal sign. They are equal as what? Yeah. Map. You have a map. You have a map. So there's a map here. That's fine. Yeah, you map.
To a column vector.
Sure. I mean, you like last time we said, any vector you can write as a cat. So you can write like this also. If you like, you can, yeah. If you have this isomorphism, that means you can work under this word also can. Work under this word also can. So you are working in the other word now, you see? When you do calculation, you calculate here.
So it's working on another space.
The space of V2.
C is the complex
thing.
thing.
Yeah. Yeah. And then you are using inner product here. So the inner product defined here is the usual one. So UTV. And this is what you do, right? UTV. This is the usual inner product here. Here should have one more inner product one. You need to figure out. I think this isomorphism should be isometric. Isometric means this distance here is preserved under this isomorphism. So that's why you can do your calculation here inside here. This one. Okay. Just I mean as what she did. So you transpose the first vector and then that one I'm not sure. That one I'm not sure. Maybe you need. I'm not sure. Yeah, this one I'm not sure. And then
Normally is the column of 1, 0 is the notation for the two-dimensional vector space.
but when you do calculation, your calculation live in vector space. I mean the usual.
No, I mean if we use the notation,
Mm.
the calculation is holds over the two-dimensional vector space, the linearity, transpose, all these things.
Mm-hmm.
The product.
Mm-hmm. Mm-hmm. Maybe you need a bar there, but bar doesn't work here, right? Because 1001, if you bar it, you still get 1001. But I'm not sure for. So what are you using then? So I mean, okay, what state you can take? For example, what state you can take? Can you take like maybe I like this? Is this a possible state or not? Okay, so I mean calculate inner product maybe between these two. Yeah, what's this inner product? I calculate.
This is just like that.
Yeah. What's the definition?
So first of all, I will take the conjugate transpose of this one.
Oh, conjugate transpose. Right. So you need conjugate transpose.
I'm curious now. So what's supposed to be the inner product for C2?
Then should be what she said. This one. You need to check this whether
the same thing.
Sorry. Sorry.
You're saying they are not different things.
They are different things.
What is
Like this, or if she say, I mean, I'm not sure, but if from what she say, I guess it's this one. Then you need to check whether this satisfies the inner product definition. What did you say? How do you compute? This?
Maybe take a conjugate transpose of this, and transpose is not
Conjugate transpose. Conjugate transpose.
what you say is from our QM side, right?
Uh-huh.
From our QM side is we are sticking with two-dimensional vector space to it's not C2.
Sure. I mean, the calculation is done. I mean, all right. Oh, I mean, wait.
mean, if you're asking how to define, how
Ah,
to define
So you are not
two-dimensional
using
vector space over C, then what is that?
yeah, I mean, yeah, that one looks plausible, but if you want to use this notation, that means you come to this word already. No, I mean, this is definition. No, here, definition. So this, if you look at this thing is defined. I mean, this is the thing that describes this word. I mean, this is the name of this. You get what I mean? So if you write like that, okay, I agree. So you are using the element here. But if you write like that, then you are using element here. You get what I mean? Right. So she explicitly write as a vector form. So I mean, this is just something there's a subtlety here. Just that's all I want to say. There's a subtlety here. Yeah. T2 is a set. Yeah. No need. I prove from here. Prove that this is a vector space. I need to. Okay, sure. Okay, sure. I mean, extra structure meaning I need to tell you how to add and then how to multiply a scalar. That's all. Yeah, I need it. Here. Here. So you have two vector. Okay, and then you conjugate transpose the first one, and then it's the same, but what I want to say is the element is different. You see, how can this be equal to this? Okay, you need to make sense of equality first. What is equal here? Equal as an element, but they are not equal as an element. Okay, because they are living in different. These two are different. They are not the same, but they are isomorphic. They are not the same, but they are isomorphic. So this is the advantage of isomorphism. You can do calculation here, also can. You draw vector, also can. But there's difference between these two. So this is a subtlety here. Yeah. So if at first you just write like this, then okay, I'm okay with this. Because you are using just you are define a genuine inner product on your vector space. But suddenly your calculation come here. But actually it works also, right? Maybe I think it works, right?
Yeah.
Because because there's an isomorphism here.
Yeah. Being precise here.
Yeah. So I mean, so you see there are two inner product here, right? So why you can calculate the inner product here using inner product here? So there's some distance preserving property inside this isomorphism actually. So there's a lot of things involved here. So you cannot just swap calculation. Yeah. But yeah, it turns out to work, I think, in this case.
So maybe he's precise enough to write like this. I mean,
Yeah.
Okay.
Yeah.
Then I can compute this.
But then you need to tell a lot of story. Why I do inner product here and people that I do inner product there. So there's a lot of story going on. So
The story of?
I mean the story of like you see. So you want an inner product on the two-dimensional vector space, but you use the inner product on C2 to calculate it. So why it makes sense? So you need to tell the story. Yeah. Otherwise, you just keep everything inside the 1, 0 is enough.
Now I want to ask the other direction, right?
Yeah.
So why is the two-dimensional vector space over C is not C2?
Not C2 because
That means that because if it's different, right? That suggests the chance that a two-dimensional vector space over C can be mapped to something other than C.
Can. Definitely. How? What else? Okay. So first of all, I want to tell you why it's not the same. So you see, the thing in here look like this. The things in here look like this. Right. Of course, they are not the same. Right. Element they are not the same. Right. Okay. So this one done. So you can say whether this is something else or not.
Yeah, we try to.
If you just consider vector space, then this is what it is. Because finite dimensional vector space characterized by basis elements. That's all. That's done. Other than that, not sure. Depend on any structure on this, the one that you consider or not. Any other structure, any other thing you want to consider.
Besides, vector space.
For example, you consider the inner product, right? So that's mean this isomorphism actually, I guess, is the isomorphism of inner product. So meaning inner product space, meaning I think this is an isometric isomorphism. Isometric, so metric is the distance. So so if you want to calculate the distance here, okay, let's call it what's state this one? What's the state? Okay, maybe put S to be equals to under this map. So I think I should write maybe UV equals to PU PV if I'm not wrong. So before you map, you get a number, right? After you map, you also can get a number. These two numbers should equal. This isomorphism should do this. This is what I call the isometric. I'm not wrong. That's what I think. Okay. So whether or not this equals to other stuff or not depend on other structure. If it is complex, then if it is vector space, then that's all. It could be equals to other thing. It could be okay. Not equal, but just isomorphic. Any bijective homomorphism. Homomorphism work for any structure. So depend on any other structure you are looking at. If it is vector space, then the story end already. Because finite dimensional vector space characterized by basis number of basis elements.
Okay. Okay.
Okay.
Okay. So this is actually the bond rule. Okay. The bond rule basically just tells us how we can actually determine the probability of a state in the eigenstate. And this is the formula that we are using. So yeah, just take the bra of the eigenstates, and then you compute it together with the cat of the state that you prepare initially. Then you just take the absolute square and you bring in. Then you find out that the eigenvalue, the absolute square of the eigenvalue turns out to be actually the probability. So you don't have to go through every steps, but you can just take the absolute square of the eigenvalue and you immediately obtain the probability. Okay, so far we have only discussed about the linear combination of eigenstates, and we can also write the states that we initially prepare as a superposition states. That means we prepare the states in a state that is more than one state, but this is just an ideal case. And in reality, when we conduct experiment, most of the time the state that we initially prepare is actually called a mixed state. And a mixed state is actually different from the state before. And the state before, we can now call it a pure state. So a pure state means, okay, so yeah, I give an example here. So for example, you have two boxes here and you put sweets inside, but there are actually two colors of the sweets. It can be blue color or it can be red color. And the box A, you actually put just a sweet, but you have no idea what color is the sweet until you actually open the box and take it out. This is actually the pure state. But for the box B, you actually put a few sweets inside these boxes, and they consist of a few number of blue sweets or red sweets, and you will have, of course, of the same thing that you don't know what is the color of the sweets that you are taking out until you open the box and take it. So here we actually I summarized the comparison as follows. So for the pure states, you only have prepare one initial pure state. And for the mixed states, you actually prepare a few states, say psi1, psi2. So when you perform the measurement on the pure states, you only perform the measurement on one state, which is the pure state. But for the mixed states, you're actually performing the measurement on psi1 and psi2. And can you actually determine which state are you performing the measurement on for the mixed states? And yes, you can. You just have to determine the probability, which is, for example, one here. The proportion, which is the proportion of the first states is actually just 5. So you can actually see here that if you perform the measurement on the initially prepared state, it's actually deterministic. But if you determine, if you perform the measurement on the mixed states, it's actually probabilistic. And how about the eigenvalue? So after you have performed the measurement on the initial states, you find that it's actually probabilistic to determine the eigenvalue for the pure states. And for example, if I want to find out what's the probability of finding the state in the eigenstates psi1, then will actually be just absolute square of a square from the Born rule. And same goes for the psi2, just b squared. Absolute square of the b. And for the eigenvalue, once you have determined what is the state that you are performing measurement on, the eigenvalue will actually be deterministic. That is, for psi1, it will definitely be just p1. So you can actually distinguish here that for the pure state, it is deterministic to perform the measurement on the initially prepared states, but it's probabilistic for mixed states. And for the eigenvalue, it is probabilistic and is deterministic for the mixed states. And there are actually few interesting properties of these mixed states. Okay, so first of all will be the average value or the expectation of any measurable quantity is actually called the observable. So say A can be like spin, momentum, or position. We will actually describe this more in the second postulate. It's actually equals to the trace of the density. The mixed state is also called a density matrix or density operator because mixed state can actually represent, statistical operator is also one of it because you can represent it in a matrix form. So the trace of this density operator times the observable will actually be the measurement of the expectation value of this observable. So this is the expectation, this is the formula for how we determine the average value. And we just apply the same thing here to determine the expectation of the observable. So the AI is actually the eigenvalue, and next to it is the probability. So by computing the following, then you obtain that it's actually in this form. And why do we want to compute this? It's because we want to make a comparison that trace of row A is also the same thing. Yeah, you can actually work it out, and this is actually in our notes. And the second interesting property is that the density operator is always greater than 0. And you can actually prove it easily by just rho, is actually the proof. And since why is it rho always greater than 0 is because at the end we will get the proportion or the probability, and since probability is always real value, is always greater than 0. And for pure state, if you take the square of the rho, it's just going to be a rho. One more, the last one will be the unit trace. So the trace of any density operator will be always equals to 1. At the final form, at the final form, the bra cat will actually equals to 1, and then the sum of probability will always equals to 1. So you get it 1. Okay. So this is for the postulate 1. So moving on to the second postulate now. Okay, the second postulate is only so the first postulate talk about the states. The second postulate is mainly going to talk about the observable. So state and observable are actually talking about the same thing, but state is represented by a cat, and observable are represented in a matrix form that is in the the brackets. So some examples of observable are just the same as the states: position, momentum, spin, and energy. So you can actually write your observable as this form, which is the eigenvalue times the cat bra. Yeah, sorry, I made the mistake just now. It's actually the cat bra. Yeah, so the cat bra. Okay, there shouldn't be an equal sign there.
Oh yeah.
So here we talk about observable can be represented by a Hermitian operator. So this is definitions of operator in mathematics. But when we apply it in quantum mechanics, the operator actually allows us to manipulate the states of the atoms. So for example, in the beginning, I have mentioned that a selector. So these are actually the formulas of the selectors that we can compute. For example, if you want to determine the spin up selector, you just take the cat bra of the states. And so first of all, how we can select the spins such that we only want to select the spin along the z-axis, x-axis, and y-axis. So we need to know what is the states of the spin along the x-axis and y-axis first. So we need a reference spin state first. I'll take here the reference spin states will be along the z-axis. So 1, 0, 0, 1. Of course, you can take different column vector, or you can take spin out along x-axis first, then you compute. But here I'm just taking spin out along z-axis first. And then I introduce here a rotation matrix. So this rotation matrix actually basically rotates the frame about the y-axis, which actually means that I'm applying an external magnetic field along this y-axis. So next, we want to determine where is the spin states along the x-axis. So if you look at the diagram, if you want to determine where is the spin states along the x-axis, we just need to rotate this spin state that is along the z-axis anti-clockwise 90 degrees. Then the spin state will be along x-axis. Yeah, just multiply the matrix with the spin states, then you get the x-axis. As for the spin states along the y-axis will be a little bit different because we can't rotate the spin along the y-axis, but we can actually introduce a new device which is called a flipper. A flipper basically means that I want to reverse the directions of the spin state, which means I apply the angle along 180 degree. It can be along anti-clock, yeah, definitely. So it will be along 180 degree, and it will still preserve the spin vector. So if you work it out, that will actually be the rotation matrix for the 180 degree. And the alpha beta is actually the spin states along the y-axis, which are unknown for now. And then there's a constant in front of it, on the right-hand side. If you work it out, this will be the spin states along the y-axis. So after you have obtained the spin states along the x-axis, y-axis, and z-axis, you can easily compute the spin up selector. And in fact, the selector are actually called the Pauli matrices. So the Pauli matrices are actually named after Wolfgang Pauli. And these Pauli matrices, you can actually show that they are Hermitians and also unitary as well. Okay, wait. Okay, yeah, these are the Hermitian operator, the properties of Hermitian operator that we have gone through. I'm not going to repeat here, but yeah, we can easily prove it here. We have done it last time as well. Yeah, and that's all from the postulate 2. And I will pass it to Alistair to continue postulate 3 and 4. It's already 8:50. I think sure.
Yeah, just no.
没有关系啊，没有看时间。好呀，你要用什么写？
白板吧。
OK。从右边。
OK，Okay, so now it's my turn about postulate 5, right? Since now it's 8:54, about to end our seminar. So I will adjust a bit for my talk, okay? Okay, so I'm going to talk about postulate 5, but in a more different way. So postulate 5 is talking about the like every quantum system has to obey the Schrodinger equations, right? So let me write it down. Please confirm. So this is the time independent Schrodinger equation, right? So talking about Schrodinger equation, like we know that it's kind of related to wave functions where most of the particle or wave have to satisfy this equation because according to the conservation of charge, right? If you study conservation of charge, conservation of charge basically means that charge cannot be created or destroyed. So as well for Schrodinger equation. So what do I mean by that? Let me draw it down. Okay. So I just briefly write it through because it's no, I mean, it's, out of time now. Okay. So now consider a system, right? Where particle is like either here, here, here. Okay. So if you only want to measure here. Okay. So according to Heisenberg uncertainty principle, right? So as the time goes on, as time increases, the probability of finding a particle at this place is decreased. So somehow, by conservation of charge, right? Somehow this place and this place, the probability of finding that particle must increase at this place so that the probability is conserved, which means it's equal to 1, right? So the continuity equation, right? Continuity equation is written in this one. I will be there equal sign, okay? Okay. So by continuity equation, right? So actually Schrodinger equation really satisfy the equation if you really prove it. So do I need to prove it if you want? Yeah, so out of time, that's all from me. Yeah.
Wait, the postulate.
It's
What's
no.
the step?
The postulate 5 is actually just states that the quantum system obeys Schrodinger equation. That's all. Yeah. So actually, for my talk today, I want to prove this. Actually, this actually like both of them are satisfied to each other.
So what's the second equation?
Oh, that's continuity equation. That okay. So I need to prove it.
No, just tell me what.
Okay. Okay. Let me write it in a more easy way.
What's rho? What's delta? What's J?
Okay. Just one thing. Okay, so here's current density. And this is my favorite charge density. And this is just nabla. Okay. So what does it mean? So when there's a current,
You need to A in terms of I, right, to connect this.
yeah.
Yeah, you need to give that. I don't ask you for proof, but you need to give a proper statement that people can correct.
J equals
Yeah.
to what? You need at least write it down, right? So
Okay. So actually J is equal to so actually J is equal to this one.
Dual of the wave function.
Yes. In the dual of wave functions.
The wave function is going from where to where? What's the domain called? Wave function.
Right? Again?
Wave function.
Mhm.
So so it's a function, right?
Yeah.
So what's the codomain? Domain.
Domain.
Yeah.
Domain.
Yeah. So what's the input? What's the output for wave function?
I remember in my memory, right? Wave function can be represented by this one. So it's a x function or either x and t.
R4.
Not R4. It's R.
R3 plus 1 x.
Can be R4. No. I don't think it's R4.
X is not the position. Position, right?
Yeah. But in this case, right, only consider one dimension. I mean,
It's okay.
free particle,
Then
I could say.
R2?
Yeah, R2.
Okay.
Yeah.
And then what? Okay. Okay. Yeah. I mean, okay. Wait. So what's U and
It's X. Sorry.
X? X and what's that? The other one?
It's
A random vector. No. X with what?
this is sign.
What size?
With the wave equation. This one. How do I write it? Is it this one? If I'm not mistaken. All right.
So they need a free particle. Are you talking about free particle?
Yeah. The free particle case.
One dimensional.
Mm.
What's A constant?
A is an amplitude. Or in this case, right,
Constant.
it's a constant. But in this case, right, if you really prove it later, actually it's a lot it actually refers to probability of in quantum mechanics.
What's the original question? What is the domain of psi? It's a complex value function. So just take x and t, and then you will calculate a complex number.
Yeah. So it's a linear function.
It's a function. Yeah. It's a linear
It
function.
should be linear. Right?
No. It's a function.
Or not linear.
No, because ax plus a constant doesn't map to linear.
A times the.
No, it's in general. No.
In general, no.
Yeah.
Because this one a bit looks like what we have just now, the Reed's representation.
Okay, so that part, because you guys haven't covered infinite dimensional Hilbert space, right? So cat psi is a infinite dimensional, is a state in the infinite dimensional Hilbert space. Then if you want to calculate So that one is normally what's called the position representation. So X is like a basis, and then you need to, because this seminar haven't defined how to calculate the inner product for this infinite dimensional, but this one is to to how to say. Yeah, cat X is like a basis, right, for this infinite dimensional space. So you take a basis element and then you inner product in the vector you project to an element, right? To that component. So this is kind of what is happening here.
But the fee, which fee, both of them are small fee and capital fee.
This is just a, which one?
So
So
the small
right hand side will be
the left hand side, both elements live in the same space.
the right hand side. So this equation is for a complex number, right? And the value of this complex number depends on position and time.
Correct. So I mean the x and the phi, small phi, is they are living in the same place.
No, they are bracket, right? They are vectors and the dual.
Right. I mean, sure. But bra is coming from the cat, right? Like what I said,
it's a dual, right?
Yeah,
It's
so
a dual.
bra
Yeah, it's
X
a
is
dual.
the dual of
the
cat X. and the cat
so
basis of-
yeah. So in that case, the x and the small phi living in the same space.
Say again?
So the x and the small phi are living in the same space.
Yes.
But why
My
the
concern is we are a bit getting this
off
off track from what you're talking about, which is the Schrodinger equation.
Oh yeah, off track. But okay.
But it's an infinite dimensional space, and then you define a.
Oh, so you use the exponential because if you use the Taylor extension, you got infinite many power of x.
No. I see. Exponential is a different story because it's a solution to some differential equation.
Can you write down the? Can you write down the? Yeah. Can you write down the exponent form of the small phi? Okay. Yeah. Huh? But this one is a thing in R3, right? No, in R in this thing. But how is this thing? This thing is not in R.
Yeah. So we are
Yeah.
off track because this is totally different story from what we are talking about. Because
I mean, he is defining wave function and this one.
no, okay. Number one, this is not true.
Okay.
This is only true in a special case where this is zero.
Free particle.
Yeah, free particle, right? So this one will not explain all this. I don't know if I want to explain all this, it will take up more time. But if we are talking about a infinite dimensional Hilbert space, right? Okay, so finite dimensional, we can express as a linear combination of the basis, right? So like this, and yeah, so this one I don't know what's the precise way to say this, but if we talk about infinite dimensional,
Even if it is finite dimensional, right, can every element express using finite sum of
or finite dimensional,
infinite? You say you are living in infinite dimensional space, right?
now I'm going to infinite dimensional. So now I'm going to write out the infinite dimensional case, right? So so infinite dimensional case, I have infinitely many bases, right? And so the way in QM is written is when you generalize to an infinite sum, it becomes like integration. So it's dx psi x, right? So then if you take an inner product, so it is the rule, the calculational rule is doing this, which is this. So this is becomes a delta function, right? The Dirac delta. So when you integrate over, you pick up this. So that's why you get something like this, right? So so this thing is kind of like the
It's
still a function of x, because we haven't said what is x yet, right? So Yeah, so it's x is arbitrary, right? But on the right hand side, for different x, you got a different x and you got a different value of the function, right? So it's a complex valued function.
So for one infinite dimensional Hilbert space, I can get one wave function.
For one dimension, for what?
For an infinite dimensional Hilbert space,
Yeah.
I can get one.
Yes.
function.
So I have an element of this infinite dimensional Hilbert space, right? Then you do this to collect its corresponding wave function. And this function, you treat it like a function in calculus, but a complex value function.
So one infinite dimensional Hilbert space produce one wave function.
No, there can be many elements, right, in this space. And each element represents different states.
So you mean there are infinitely many solutions to that inner product equality?
Yeah,
There are infinitely many solutions.
because because these are just elements of a vector space, right? This particular Hilbert space. And the postulate of quantum mechanics says that to say that it must obey this Schrodinger equation, because you can actually relate this to a unitary operation in this infinite dimensional Hilbert space, but you need to do a bit more work to show this.
So need to satisfy this inner product, need to satisfy that Schrodinger equation.
Yes.
Wave function.
Yes. Yes, and some are actually related.
Implication. If you satisfy that, then you can.
Yeah, I think so.
If and only if.
I forgot. I can't recall. Yeah, probably something like that. But
And then this inner product equality translate to the conservation of charge.
no, because this one just gives you a function, right?
Okay.
And it could be any function, right? But the postulate is telling us that this function must satisfy this differential equation. And then so this equation is that J is given by this, rho is this thing, right? So using this function psi, right? I can get rho, and then I can construct the J like this, right?
Oh, equivalent.
Yes. So this plus this equals to 0. And to show that this equals to 0, we need to assume that this rho satisfies this Schrodinger equation.
So in this case, the t is 0, just like you mentioned.
No, t can. So
how you get a number if you don't have substitute t into your wave?
So let's say there is one of these at every t. Because because it's time dependent. So at every t there is a.
Oh, okay. Oh, okay. But this is time dependent for the equation, right?
Time dependent, right?
Oh, yeah. So, but you don't integrate over time, then how the time variable disappear?
Right. So no, I think for simplicity, we just think of it as evaluate over one time. So this is at one instant of time. Yes. Then
evaluate.
Yes, we do this during one fixed time.
Okay.
Yeah.
I mean, I don't talk too much. It's already time. Yeah, it's already time. The problem is, you guys want to continue or dinner or Q&A? You guys want to continue proving this or Q&A or just go for dinner?
Go dinner.
Dinner. Go dinner and prove to you. Why not? Yeah. Q&A. Yeah.
The turn dialect
experiment, no matter what magnetic field you put on, you always get two dots.
Zero atoms.
Of a single atom. Others,
Others
field discrete
would be accurate.
won't be accurate.
Because the reason why we choose zero atoms is because like from chemistry side
Oh,
you only have that one electron, so you just study like that one electron.
okay.
But for like others like let's say like
Two, like, let's say go to two.
go to one, then very messy the calculation.
I mean, what's the pattern you see on the screen?
Spin half, you give me in the spin is 3 halves in the thing. But because these are like yeah, it depends on the spin. Okay, right? And because the silver atoms happen to be consist of construct of these many protons. So you sum up all these protons and then you get this number of spin. So you can build up different protons and you get a different.
Or not because of the single electron on the outer core.
It's no, right? No. Yeah, it's the nucleus.
Oh, it's the nucleus. I thought just now she meant
Yeah,
like
I thought like
Yeah, but what if they are excited about this higher states? Because otherwise you get all the ground states, or you can get like all the different states. Actually, I forgot, so I'm not 100% sure. Or it's true, we need, so this teaches us that we must be careful the difference between spin angular momentum, orbital angular momentum, right? I guess we should probably check the Stern-Gerlach is actually picking up the spin of the orbital.
This way, they say like so there's a lot of orbits inside but the reason why they choose zero is because there's only one electron on the very outside. The other one is like occupied only in the orbits. They claim it's stable, so it won't contribute anything to like the electron dynamics of atom itself. So I think that's the reason because there's only one electron, and because zero is quite cheap compared to other elements. That's the reason.
But if it's one orbital, then you can have the SPDF orbital.
yeah, it's actually because of the electronic configuration. Atom is actually 4s1. S electron is S orbital. But of course, yeah.
S is the zero spin, right?
Uh,
Zero angular one.
Yeah. So I think it does not exactly means that she atom only has one electron. Why only zero?
they say it's cheap on speed. Hydrogen is reactive.
Pure hydrogen. As you can just grab it from the ground.
So why the classical say must be continuous?
From the classical
Oh.
formula.
Oh.
So L equals to mv. So velocity is continuous. So angular momentum must be continuous, just like velocity.
Implication.
It can take many possible values.
It's running low. Face running low.
Yeah, 我看电脑。Yeah. Oh, shit. Okay.
Hello. All right. Sorry for the insufficient time just that I couldn't prove a lot of things, right, and cannot mention clearly. But since this is the end of our seminar, right, I would like to. Okay, so this is our feedback form. Kindly scan it, and there are some questions inside the questionnaire. So feel free to give some feedback so we can improve better in the next seminar. I mean, in future. So I think 2 minutes is enough, maybe.
That's generally question like unless you can explain the question for the items.
You guys done feeling? Alright, I think this is the end of seminar. But some things that I would like to tell is like this is not the end of the journey. So there are more things, more seminars or more I could say is academic related that will be held in the future semester. And I hope this is kind of like helpful to each of you. Yeah. So basically what I want to tell is uh I hope how to say seminar is not the end of journey because curiosity is always there. It's always there. And you guys, I mean, not you guys, I mean, each of us, I mean, every one of us have to be really curious of what we are trying to learn and solve the unsolved issue in this world. And normally the answers come from discussions or maybe a dream, like Kissing say, a dream. Okay, so the final message is for me is like never stop asking questions. So question is it's a process and it's a procedure that leads you to solve any problem that still haven't been solved in this world yet. All right. So thank you everyone. Right, so guys, ready? Stand up. Thank you, Dr. Thank you, Dr. Lee. Thank you, Dr. Lee. Not me. Thank you, Alistair.
Suddenly everyone talking.
On is 还没有 stop。